Hey guys, Ms. Peterson here, and welcome to our Physics in the Universe lecture on light. Okay, we've already looked at how we model light and how we can think about it in terms of waves and particles, depending on what we're talking about. We learned about the behaviors of light and compared those to the behaviors of particles and transverse waves and sound waves. And now let's get some of that basic information down in our notes. So, what is light? Now, most of the time, the definition that's going to work well for us is that light is a transverse wave of oscillating electric and magnetic fields. Remember, oscillating just means moving back and forth, so these are changing electric and magnetic fields. And all waves are caused by vibrations. What is vibrating specifically to cause light waves is electrons. So it is the subatomic particle of the electron in atoms vibrating and moving up and down between its different energy states that can produce light. Okay, so basically, because it is that electric field and the magnetic field, both of those are perpendicular. This wave would be moving like along this x-axis there. And yeah, because of that, we call it an electromagnetic wave because it's got the electric fields and the magnetic fields. And since it's not moving matter like our mechanical waves, it doesn't need a medium to travel with. Which makes sense. If it needed a medium, then how would sunlight reach us from outer space, okay, or the stars? We can see all of those things, so we know light travels through the vacuum of outer space. Okay. However, sometimes we need to use a particle model of light. And when we use a particle model of light, we call those particles of light photons. Okay. Sometimes one model will be more useful than another, but it has that duality, so we can use both. And the speed of light is a constant. Technically, this is the speed of light in a vacuum, which is also the speed of light in air. Anything else that you would see light in, like glass or things like that, it would have to tell you the speed of it, and you're unlikely to see it in this class. So for us, we have the speed of light. It is so special, it even gets its own letter, okay? The velocity of light, normally we use V, is c, 3.00 times 10 to the 8th meters per second. Okay. Okay, cool. So how do we classify light waves? Well, they're organized by wavelength into something called the electromagnetic spectrum. Okay. And we're going to look at that in a sec. But an important thing to note about it is that visible waves, the kind of light that we see with our eyes, is only a teeny part of the electromagnetic spectrum. Okay? If we could see all of the information around us, imagine being able to see all the radio waves from every single radio station and all of our communication waves. Okay? Those are normally in radio or microwaves coming from all of our phones, sending out and gathering information in the Wi-Fi. Imagine if we could see all that information. That'd be weird, okay? We only see the visible light information. And we feel the infrared radiation on our skin and the UV. Now, the brightness of light waves is related to the amplitude of the light wave, and or you can think of it as the amount of photons, depending on if you're thinking in a wave or particle model. Okay. Now let's go ahead and look at this electromagnetic spectrum a little bit closer. Okay, this is what it looks like. So we can see visible light right here, which is on the order of wavelength of 10 to the minus 6. Okay, we normally measure it in nanometers, where visible wavelength has 400 to 800 nanometers. So it's right in this little range. Things that have less energy of it, okay, this is in order from lowest energy to highest energy, which is the lowest frequency to the highest frequency, but backwards, remember, in terms of wavelength. So radio waves have the longest wavelength. Their waves are long and on the order of magnitude of like a house or a soccer field. Okay, that's how big one radio wave is. Where things like ultraviolet rays are on the order, their wavelengths are on the order of magnitude of like viruses and proteins. And that's why they can affect the proteins in our skin. Okay, you can get a sunburn because the ultraviolet light interacts with stuff in your cells, in your skin, and causes that reaction, okay? And that's an important thing to note. In order for a wave to interact with something, normally its wavelength has to be on about the same order of magnitude. Okay, so like infrared, we feel as heat because it can interact with our cells. Where like we don't aren't really affected and don't notice the radio waves all around us because they're way too big, okay? They're an order of magnitude like bigger than us. So we wouldn't really affect them, okay? This is also a great argument in case you ever see people on, say, like the internet complaining about the dangers of 5G, okay, the dangers of your cell phone. Well, your cell phone emits radio waves, okay? And radio waves are lower in energy than microwaves, which is lower in energy than infrared waves, which is lower in energy than light waves. And we never complain about all the like yellow radiation around, okay? All of this yellow radiation. It's still the same stuff. It's just higher in energy than, say, infrared or 5G, okay? It's just all different variations of the same things, okay? So let's go ahead and talk about color. What's color? So different colors are just different wavelengths of light. They have different amounts of energy. An important thing to note about this is that something is green because it absorbs wavelengths other than green and reflects the green back to your eye. So it's not green, okay, like this green screen I have behind me. It's not green because it is absorbing all of the green and becoming green. No, it's green because it's reflecting the green back to you. The green is what it is giving to you so your brain can absorb that information. Okay, cool? Okay, cool. We do need to know the colors in order. So red is the longest wavelength, and purple is the shortest. Okay, and again, we use that lambda for wavelength. So wavelength increases as you go towards red. Okay, but that is the opposite trend for frequency and period. So for frequency, red has the lowest frequency, where purple has the highest. Okay, which makes sense. All of these are light waves, so they all travel at the same speed. If you have a long wavelength, I'm going to see less of you per second, okay? Because if you're going at the same speed by and you're nice and long, I'm going to see less. Versus if you have a short little wavelength, I'm going to see more going by each second. Okay? And then the last is the energy. So red is the lowest energy, and purple is the highest energy. The way that I like to remember this one is if you just think of it in terms of infrared and ultraviolet, infrared is below red, okay? And that isn't dangerous, okay? Infrared, we can see those with night vision goggles, and it's just the heat given off by our bodies. So it's just heat, that's not dangerous. But past purple, we have ultraviolet rays. Ultra, past purple. Ultraviolet rays can be dangerous, okay? Those are the ones that can cause sunburns or skin cancer if you have too much exposure to them. So that's the way I remember it. And then white light is a mixture of all of the colors, okay? So something that looks white reflects all colors equally, where something that appears black absorbs all colors equally. Let's go ahead and do some example problems. A microwave has a wavelength of 6 centimeters. Okay, so it has a wavelength of 6 centimeters. Okay, find its frequency. Well, that doesn't seem like they give us a lot of information. Okay, they only gave us one number. But a microwave is light. Okay, remember, we're in physics. So in physics, light isn't just the light that we see, it's the whole electromagnetic spectrum. So it can be radio waves or gamma rays or infrared or ultraviolet or yellow. Okay, and they all travel at a velocity equal to the speed of light, which is 3.00 times 10 to the 8th meters per second. Okay, so what equation are we going to use? Well, we have V. We have wavelength, and we're looking for frequency. So that's only one unknown in V equals frequency times wavelength. Okay, the speed of a wave equals its wavelength times its frequency. So if I'm solving for the F here, I would divide both sides by that wavelength. So then my equation becomes that the frequency equals the velocity divided by the wavelength. But I'm not quite ready to plug in yet. Why not? Well, I need to convert. I have my velocity in meters per second, but my wavelength is in centimeters, okay? And I need those units to match up. Two different ways you could think of this conversion. Okay, first we can do it the classic way, where we know that there are 100 centimeters per each 1 meter. We're dividing it by 100 and get 0.06 meters. You can also remember that the prefix centi means 100th, or 10 to the negative 2. So 6 centimeters means 6 times 10 to the negative 2 meters, which is what we see there. Okay, but now that our units agree, meters, we're ready to plug into our equation. So my velocity is 3.00 times 10 to the 8th meters per second divided by my wavelength, 0.06 meters. Meters and meters cancel off, and you get, plug it into your calculator, 3, using that EE button, which means that times 10 to the 8th divided by 0.06, and I get 5 times 10 to the 9th per second. So we remember that a per second is a hertz. So the frequency of that microwave would be 5 times 10 to the 9th hertz. Let's do another one. Okay, so a radar, which is a radio wave signal, is pointed at the moon, and a reflection is received 2.57 seconds later. How far away is the moon? Okay, so let's first make sense of the problem. We got the moon over here. Okay, there's my moon. Okay, it's got some craters on it, yeah. And then there's my satellite, and it's going to send a signal to the moon and then receive it back. Okay, and we know that that is going to take a time of 2.57 seconds. Okay, radar, radio wave, so we know it travels with a speed of 3.00 times 10 to the 8th meters per second, and we're looking for how far away is the moon. So we're looking for some distance there, x. Okay, now, if I just plugged in these numbers and solved for x, that would be the distance to the moon and back. Okay, so I have two options. I could either solve for that x and then divide by 2, or I could divide this time by 2 now to get just the distance, just the time to the moon. I think I'm going to actually do it with the numbers that they gave me and start from there. So this time I have v, x, and t, okay, not wavelength and frequency. So I'm going to use velocity is distance over time. And if I'm solving for my distance, I will multiply both sides by time to get that distance equals velocity times time. I have seconds and seconds, so my units look good. I'm ready to go ahead and plug in. Okay, I have x equals my velocity, 3.00 times 10 to the 8th meters per second times 2.57 seconds. And that gives me 3 times 10 to the 8th times 2.57. That gives me 7.71 times 10 to the 8th meters. Okay, but this is to the moon and back. Okay, because that's how long this 2.57 seconds was for. So if I want to get just the distance to the moon, I would do that number and divide it by 2. Okay, so when I do that, I get 3.855. So I'll just keep it at 3.85 times 10 to the 8th meters. Okay, cool. Okay, cool. That's for our light lecture.